Deep in the Siberian Taiga lie secrets that could change our understanding of 20th century history. Hundreds of nuclear explosions turned endless forests into a radioactive desert. But the truth about this catastrophe remains classified to this day. Millions of people were exposed to deadly radiation. Entire ecosystems were destroyed. And we are still feeling the consequences of these experiments today. Today, we will talk about the nuclear legacy that will affect the fate of our planet for many centuries to come. Subscribe to our channel to support it and learn more about the secret facts of history. What do you think about the moral responsibility of the scientists who created nuclear weapons? Should they have refused to participate in these experiments, knowing their consequences? Share your opinion in the comments. Deep in the Siberian Taiga, among endless forests and swamps, events unfolded in the middle of the 20th century that forever changed the face of our planet. While the world was still reeling from the horrors of World War II, a new era was dawning in the secret laboratories and classified testing grounds of the Soviet Union, the atomic age. On August 29, 1949, the first Soviet nuclear explosion rocked the steppes of Kazakhstan. Operation First Lightning marked the USSR's entry into the nuclear club, but it was only the beginning of a grand and tragic story. What followed this historic moment remains one of the most secret pages of Soviet history. The nuclear testing program in the USSR developed at an unprecedented speed. While the Americans conducted their experiments in the deserts of Nevada and on Pacific atolls, Soviet scientists chose a completely different path. They decided to use the vast expanses of their own country, from the steppes of Kazakhstan to the Arctic archipelagos, from the Ural Mountains to the Siberian Taiga. Igor Kurchatov, chief designer of the Soviet atomic bomb, understood that hundreds of tests would be required to create a full-fledged nuclear arsenal. But where could they be conducted in a country where most of the territory was populated? The solution turned out to be cynical in its simplicity. Use regions that were considered insignificant from the point of view of the central government. The creation of a network of nuclear test sites began even before the first test. Classified documents, many of which only became available in the 1990s, contained plans to turn vast territories into areas of radioactive contamination. But the most frightening thing was that no one had calculated the long-term consequences of these experiments. The Semipalatinsk region of Kazakhstan was chosen as the site for the main test site. On August 18, 1947, a decree was signed to create the USSR Ministry of Defense's Training Ground Number 1. This innocent name concealed a gigantic complex for testing nuclear weapons covering an area of more than 18,000 square kilometers. Initial geological surveys showed that the region's subsoil was rich in various minerals, and that the area itself was sparsely populated. This seemed to be the ideal combination for secret experiments. However, even then, some scientists warned of the possible environmental consequences. Their voices were drowned out by the state machine, for which geopolitical ambitions were more important than the safety of its own population. The construction of the test site was carried out in strict secrecy. Tens of thousands of prisoners, military builders, and civilian specialists were involved in this work. Many of them did not even suspect that they were participating in the creation of a facility that would become a symbol of the nuclear arms race. How many of these people subsequently suffered from radiation exposure remains unknown. Additional test sites were created in parallel with the main test site. The Novaya Zemlya archipelago in the Arctic was chosen for testing particularly powerful charges. The Totsi test site in the Orenburg region was intended for exercises involving tactical nuclear weapons. Each of these facilities was a small town with its own infrastructure, scientific laboratories, and residential areas. The creation of nuclear infrastructure required not only enormous material costs, but also the mobilization of the country's best scientific personnel. Graduates of leading universities, experienced engineers, and young physicists were sent to the secret laboratory cities. Many of them devoted their entire lives to this work, without even suspecting the scale of the tragedy in which they were participating. The first underground nuclear tests in the USSR were conducted as early as the 1950s. The technology of underground explosions seemed safer than atmospheric tests, but this was only an illusion. Radioactive decay products penetrated the groundwater, contaminated the soil, and spread through food chains hundreds of kilometers from the epicenter of the explosion. The technology of underground nuclear explosions seemed revolutionary. Unlike atmospheric tests, which created the famous mushroom clouds visible for hundreds of kilometers, underground explosions took place in deep mines or wells. Soviet engineers believed that the Earth's crust would be a reliable barrier to radiation, but the reality turned out to be much more complicated. The first underground test in the USSR took place on October 11, 1961, at the Semipalatinsk test site. A nuclear device with a yield of about 1 kiloton was placed in a mine 190 meters deep. The explosion created an underground cavity with a diameter of about 30 meters and a crater 6 meters deep formed on the surface. Scientists observed the experiment from a bunker located several kilometers from the epicenter. Seismographs recorded underground tremors comparable to an earthquake of magnitude 5. But what happened to the radioactive substances underground remained a mystery even to the organizers of the test themselves. The principle of an underground nuclear explosion was based on creating enormous temperature and pressure in a confined space. At the moment of detonation, the temperature at the epicenter reached tens of millions of degrees, instantly turning the rock into plasma. The resulting cavity was filled with hot gas and molten rock, which cooled to form a glass-like mass containing radioactive isotopes. Soviet physicists working on this program understood that underground explosions would allow them to test more powerful charges without attracting international attention. Atmospheric tests were easily detected by other countries' radiation monitoring systems, while underground explosions remained hidden from the outside world for a long time. However, the first experiments already revealed serious problems with sealing. For several days after the explosion, radioactive gases were released from cracks in the ground. Particularly dangerous were isotopes of iodine, strontium, and cesium, which easily penetrated the atmosphere and were carried by the wind over long distances. Technical specialists at the test site kept detailed records of each test. The archives contain reports describing not only the parameters of the explosions, but also their unforeseen consequences. For example, after a test in March 1962, a radioactive cloud reached the city of Semipalatinsk, located 150 kilometers from the test site. The development of underground testing technology was carried out in parallel at several research institutes. The Institute of Experimental Physics in Sarov, the All-Russian Scientific Research Institute of Technical Physics in Snezhinsk, and other closed centers competed in creating more sophisticated methods for conducting nuclear experiments. But the main problem remained that no one had studied the long-term effects of radiation on the taiga ecosystems. Scientists focused on the technical aspects of the explosions, leaving environmental issues in the background. This decision had catastrophic consequences that are still evident today. Gradually, the power of underground tests increased. While the first explosions were measured in kilotons, by the end of the 1960s, megaton-class charges were being tested. Such explosions created underground cavities the size of a multi-story building and caused seismic vibrations that could be felt hundreds of kilometers away. One of the most ambitious projects was a program to create artificial underground reservoirs using nuclear explosions. In theory, such cavities could be used to store oil, gas, or even drinking water. In practice, all such experiments led to the radioactive contamination of huge volumes of groundwater. The personnel at the test sites worked in conditions of constant radiation risk. Despite the use of protective suits and dosimeters, many specialists received doses of radiation that exceeded safe levels by tens of times. The medical records of these people are still classified, which makes it impossible to assess the true scale of the tragedy. By the mid-1970s, the technology of underground nuclear explosions had been perfected. Soviet specialists learned to control the power of the explosion, the direction of seismic waves, and even partially prevent the release of radioactive gases to the surface. But the price of this technical progress was monstrous. Thousands of square kilometers of taiga were turned into a radioactive desert. The map of the Soviet Union's secret nuclear test sites was a geography of fear stretching from the western borders to the Pacific Ocean. Test sites were scattered across a vast territory from the Baltic Sea to Kamchatka, each with its own specialization and secrets. The Semipalatinsk test site in Kazakhstan remained the main arena for nuclear experiments, but it was far from the only one. The Novaya Zemlya test site in the archipelago in the Barents Sea was used to test thermonuclear weapons of special power. It was here that on October 30th, 1961, the Tsar bomb was detonated, the most powerful nuclear device in human history. But there were also lesser-known test sites, information about which remains fragmentary to this day. The South Ural test site, officially called Object Number 810, was located near the city of Snezhinsk. Here, small nuclear charges were tested, and technologies for their safe transportation were developed. The most secretive remained the northern test site, located on the Novaya Zemlya archipelago. Its existence was not officially recognized until the early 1990s, although local residents, the Nenets and Pomors, had long been aware of the strange flashes of light and underground tremors that regularly occurred in these areas. The geography of nuclear testing was determined not only by military considerations, but also by geographical factors. Semipalatinsk was chosen because of its remoteness from large cities and relatively stable climatic conditions. Novaya Zemlya was attractive because it offered the opportunity to conduct tests above the sea surface, which made it possible to study the impact of nuclear explosions on the aquatic environment. Less well-known test sites were created for specific tasks. The Totsky test site in the Orenburg region was intended for military exercises involving tactical nuclear weapons. On September 14, 1954, the only experiment in the USSR involving live human subjects was conducted here. The Krasnoyarsk territory was home to the secret Yenisei test site, where nuclear charges were tested for peaceful purposes. The nuclear explosions for the National Economy Program envisaged the use of atomic energy to create artificial reservoirs, lay canals, and even extract minerals. Each test site had its own infrastructure and staff. Closed cities with their own hospitals, schools, and scientific laboratories were built around the test sites. Thousands of specialists, from nuclear physicists to builders and cooks, lived in strict secrecy, not even allowed to tell their relatives about the nature of their work. But the worst thing was that many of these sites were located in areas traditionally inhabited by indigenous peoples. Kazakh Owls near Semipalatinsk, Nenets settlements on Novaya Zemlya, Evenk settlements in the Siberian Taiga. All of them ended up in the radiation zone. The transport logistics of nuclear testing required the creation of a special infrastructure. Secret railway lines were laid to remote test sites. Airfields were built for the transport of top-secret cargo, and special motorways with a system of passes and security were created. The coordination of the work of various test sites was carried out from Moscow through a network of secret research institutes. The Kurchatov Institute, the All-Union Scientific Research Institute of Experimental Physics in Sarov, the All-Union Scientific Research Institute of Technical Physics in Snezhinsk, and other centers developed a common strategy for nuclear testing and shared the data obtained. The communication system between the test sites used special channels protected from interception. The test results were transmitted in encrypted form and stored in special archives with a multi-level access system. Many of these documents remain classified to this day. The environmental impact of nuclear test sites was studied only fragmentarily. The main focus was on the military technical aspects of the tests, and data on the radiation contamination of natural ecosystems was classified as a state secret. As a result, the true scale of the environmental disaster only became known decades after the end of the nuclear program. By the end of the 1980s, there were more than a dozen nuclear test sites for various purposes operating in the USSR. The total area of contaminated territory amounted to tens of thousands of square kilometers, and the number of tests conducted was estimated in the hundreds. This invisible network of radiation contamination enveloped the entire country, creating a slow-acting ecological bomb. The Semipalatinsk test site became a symbol of the Soviet nuclear program and, at the same time, the epicenter of one of the greatest environmental disasters in history, disasters of the 20th century. Located in the steppes of eastern Kazakhstan, this gigantic complex, covering an area of 18,500 square kilometers, served as the main arena for nuclear weapons testing for 40 years. The history of the test site began on August 21, 1949, when at 6 o'clock in the morning local time, the mushroom cloud of the first Soviet atomic bomb rose above the Kazakh steppe. The explosion had a yield of 22 kilotons, almost 1.5 times greater than the bomb dropped by the Americans on Hiroshima. The choice of location for the test site was determined by several factors. First, it was a sparsely populated area, home to only about 20,000 people, mainly Kazakh cattle breeders. Second, the flat steppe terrain made it easy to monitor the results of the explosions. Third, the continental climate with minimal precipitation reduced the risk of radioactive substances spreading. However, the organizers of the test site completely disregarded the interests of the local population, who effectively became hostages to the nuclear experiments. Residents of nearby villages were not warned of the danger and received no information about the tests being conducted. Many of them only learned of the existence of the test site after the first explosion, when their homes shook from the shock wave. Over 4 decades, 456 nuclear explosions were carried out at the Semipalatinsk test site. Of these, 116 were atmospheric, 25 were ground-based, and 315 were underground. The total power of all the charges tested exceeded 250 megatons, which is 12,000 times more than the bomb that destroyed Hiroshima. Atmospheric tests conducted until 1963 caused the most damage to the environment. Radioactive clouds spread for hundreds of kilometers, contaminating vast areas. Particularly devastating was the test on August 12, 1953, when the first Soviet hydrogen bomb with a yield of 400 kilotons was detonated. Underground tests, which were considered safer, actually created no less serious problems. Radioactive substances penetrated the groundwater, contaminating artesian wells at a depth of up to 100 meters. Many wells in the surrounding villages became unusable, but the local residents were unaware of this. The test site's infrastructure included several test areas, each with its own purpose. The experimental field site was used for atmospheric explosions, Deglin for underground tests in the mountain range, and Balapan for underground explosions in the steppe. In addition, there were specialized areas for testing the effects of nuclear explosions on various materials and structures. The test site's scientific staff numbered several thousand people. The closed city of Kurchatov, built specifically to serve the test site, was home to nuclear physicists, engineers, military specialists, and service personnel. The city was completely isolated from the outside world and had its own life support system. Medical research on the effects of radiation on the local population was conducted in strict secrecy. Doctors working in the test site area were required to conceal the true causes of diseases and were not allowed to mention the link between diseases and radiation exposure in medical records. As a result, thousands of people did not receive the necessary treatment. The environmental consequences of the test site's activities became apparent very quickly. As early as the 1950s, scientists recorded mass livestock deaths in areas adjacent to the test sites. Animals were born with deformities, lost their fur, and developed tumors. But all this data was classified and did not make it into the open press. The taiga's plant life also suffered from radiation exposure. Trees within a radius of several kilometers from the epicenters of the explosions died or became deformed. The soil in large areas became unsuitable for agriculture, but the farmers were not informed of this. By the end of the test site's existence, the level of radiation contamination in some areas exceeded background levels by hundreds of times. Isotopes of plutonium, cesium, strontium, and other radioactive elements penetrated deep into the region's ecosystem, creating a long-term threat to all living things. The half-life of some of these substances is thousands of years, which means that vast areas have effectively been turned into exclusion zones for an indefinite period of time. On August 29, 1991, the Semipalatinsk test site was officially closed by decree of Kazakh President Nursultan Nazarbayev. But the radioactive legacy of this place continues to affect people's lives 3 decades after the last test. The Novaya Zemlya archipelago in the Arctic Ocean became the second most important nuclear test site in the Soviet Union, a place where the most destructive weapons in human history were tested. The harsh Arctic conditions and complete isolation from the outside world made this region ideal for secret experiments with thermonuclear weapons. The Novaya Zemlya test site was created in 1954 to test particularly powerful nuclear devices that could not be detonated on the mainland. The archipelago, located between the Barents and Kara Seas, consisted of 2 large islands with a total area of 83,000 square kilometers. a territory comparable to Austria. The climate of Novaya Zemlya is extremely harsh, even by Arctic standards. The average winter temperature drops to -30 degrees, and the polar night lasts more than 2 months. In summer, the temperature rarely rises above +5 degrees. Constant winds, fog, and blizzards made life on the archipelago extremely difficult. But it was this isolation that attracted military planners who saw Novaya Zemlya as an ideal testing ground for weapons of mass destruction. The local population, the Nenets and Pomors, who traditionally engaged in reindeer herding, hunting, and fishing, numbered only a few hundred people. No one took their interests into account. Construction of the test site began in the polar winter. Building materials and equipment were delivered by sea during the short navigation period or by plane via mainland bases. The workers, mainly prisoners from correctional labor camps, labored in inhuman conditions at temperatures as low as -40 degrees. The first test on Novaya Zemlya took place on September 21, 1955. It was an atmospheric detonation with a yield of 1.5 kilotons carried out from a ship in Chernaya Bay on the southern island of the archipelago. The explosion created a radioactive cloud that drifted over the Arctic seas for several weeks. The most famous test on Novaya Zemlya was the explosion of the Tsar Bomba on October 30, 1961. A thermonuclear device with a yield of 58 megatons was dropped from an aircraft over the test site in the Sukhoi Nos area. The fireball from the explosion reached a diameter of 4.5 kilometers, and the mushroom cloud rose to a height of 67 kilometers. The shockwave from the Tsar Bomba explosion circled the globe 3 times. The light radiation was visible at a distance of more than 1,000 kilometers. Even in Norway and Finland, people observed a strange glow on the northern horizon. Seismic stations around the world recorded underground tremors measuring 5.5 on the Richter scale. The impact of such a powerful explosion on the Arctic ecosystem was catastrophic. All vegetation within a radius of several tens of kilometers was destroyed. The ice cover of the seas cracked over a huge area. Many species of Arctic animals disappeared from the archipelago forever. A total of 132 nuclear explosions were carried out at the Novaya Zemlya test site. 87 of them were atmospheric, 42 were underground, and 3 were underwater. Underwater tests were conducted in the bays and gulfs of the archipelago to study the impact of nuclear explosions on the marine environment. The test site personnel were housed at a mainland base in the village of Belushya Guba on the southern island. Residential buildings, administrative buildings, scientific laboratories, an airfield, and berths for military ships were built here. Communication with the mainland was maintained via radio stations and regular flights. Scientists working on Novaya Zemlya studied not only the military aspects of nuclear explosions, but also their impact on the climate and ecosystems of the Arctic. However, the results of these studies remained classified. It was only decades later that the extent of the environmental damage caused by the tests became known. The indigenous population of the archipelago, the Nenets reindeer herders, were forcibly resettled to other areas even before the tests began. Their traditional pastures and hunting grounds were turned into a radioactive desert. Many families lost touch with their homeland and traditional way of life forever. The marine environment around Novaya Zemlya also suffered from radiation contamination. Underwater explosions created areas of high radioactivity in the bottom sediments. Fish and marine mammals accumulated radioactive isotopes in their tissues, making them unsafe for consumption. The last test at the Novaya Zemlya test site was conducted on October 24, 1990. After that, the test site was officially closed, but radioactive contamination of the territory remains a problem to this day. The half-life of some isotopes formed during the explosions is thousands of years. Today, Novaya Zemlya remains a closed territory. Access to the archipelago is restricted by special permits, and most of the territory is still considered dangerous for human habitation. Arctic nature is recovering very slowly from the radiation shock, and it may take centuries for the ecosystem to fully recover. On September 14, 1954, an event took place in the steppes of the Orenburg region that forever changed perceptions of the acceptable limits of military experiments. The Taiga exercises became the only nuclear weapons test in the history of the USSR involving living people as test subjects. The Taiga test site was located 150 kilometers from Orenburg, in a deserted steppe area. Officially, the exercises were called an experiment to test the tactics of troops in conditions of nuclear weapons use. In reality, it was a grand experiment to study the effects of an atomic explosion on manpower and military equipment. 45,000 people took part in the exercises: soldiers, officers, civilian specialists, and scientists. Most of them did not know the true purpose of the experiment and believed that they were participating in routine military maneuvers. Only a limited circle of senior commanders had full information about the planned real nuclear explosion. Preparations for the exercises took several months. Various fortifications were built at the test site. Military equipment was deployed, and mock military towns were created. Not only humans were used as test subjects, but also thousands of animals: dogs, pigs, rats, and mice, which were placed at various distances from the epicenter of the future explosion. A 40-kiloton atomic bomb was detonated at an altitude of 350 meters above the center of the test site at 9:33 a.m. The temperature at the epicenter of the explosion reached several million degrees. The light radiation was so intense that soldiers in trenches 6 kilometers away from the explosion suffered burns to their retinas. Immediately after the explosion, the second phase of the exercises began: the attack on the enemy positions. Red Army units under the command of Marshal Georgy Zhukov began their advance through the epicenter of the explosion. The soldiers attacked through an area where the radiation level exceeded lethal levels by tens of times. The soldiers were not given any radiation protection equipment. Moreover, many of them were dressed in summer uniforms, which did not provide even minimal protection from radioactive particles. The soldiers breathed contaminated air. Their skin came into contact with radioactive dust, and they drank water from contaminated sources. Within a few hours after the explosion, the troops passed through the epicenter and secured the opposite side of the training ground. Official reports claimed that the exercises were successful and that all participants were feeling well. In reality, within a few days, many soldiers began to show symptoms of radiation sickness. Medical care for the participants in the exercises was organized under the strictest secrecy. Doctors were forbidden to make diagnoses related to radiation damage. Other illnesses, ranging from colds to stomach upsets, were recorded in the soldiers' medical records. The true causes of their ailments were hidden even from the patients themselves. Animals used as biological detectors died en masse in the first days after the explosion. Those that survived showed all the signs of severe radiation damage: hair loss, internal bleeding, and impaired coordination. But the results of these observations were also classified. The Totsky test site became unsuitable for economic use for many years. The level of radiation contamination of the soil, vegetation, and water bodies exceeded safe limits by hundreds of times. However, the local population was not warned about this, and farmers continued to graze livestock and grow crops on the contaminated land. Georgy Zhukov, who led the exercises, later said that the experiment provided important information about the possibility of conducting military operations in a nuclear war. But the price of this knowledge turned out to be monstrous. Thousands of people were exposed to deadly radiation to satisfy scientific curiosity and military ambitions. The long-term consequences of the Totsky exercises manifested themselves over many years. Participants in the experiment were 2 to 3 times more likely to develop cancer, leukemia, and other diseases associated with radiation exposure. Their children were born with congenital malformations, but official medicine denied any connection between these problems and participation in nuclear exercises. The declassification of materials on the Totsk exercises began only in the 1990s. It turned out that the experiment was planned as the first in a series of similar tests. Fortunately, public outrage and protests by scientists forced the military leadership to abandon further experiments involving humans. Today, the territory of the former Totsky test site has been partially restored for economic use. However, in some places, the radiation level still exceeds background levels. A monument to the participants of the Totsky exercises was erected only in the 2000s, half a century after the tragic events, when most of the witnesses were no longer alive. In the 1950s, one of the most ambitious and at the same time destructive ideas in human history was born in the Soviet Union: the use of nuclear explosions for peaceful purposes. The Nuclear Explosions for the National Economy program, officially launched in 1958, envisaged the use of atomic energy to solve grandiose engineering problems. The concept of peaceful atoms seemed revolutionary. Soviet scientists proposed using nuclear charges to create artificial reservoirs, lay canals, extract minerals, extinguish gas fountains, and even change the course of rivers. Theoretically, a single nuclear explosion could replace millions of tons of conventional explosives and accomplish work that would otherwise take years and enormous labor. The first peaceful nuclear explosion in the USSR was carried out on January 15, 1965, as part of the Chagin project. The aim of the experiment was to create an artificial lake using an underground nuclear explosion with a yield of 140 kilotons at the Semipalatinsk test site. The explosion created a crater 400 meters in diameter and 100 meters deep, which was filled with underground water. However, it became clear from the outset that peaceful nuclear explosions were no less dangerous than military tests. The resulting Chagin Lake was so radioactive that its water was unsuitable for any use. The level of radiation in the water exceeded permissible limits by 1,000 times, and the shores of the lake became deadly dangerous for humans. The program of peaceful nuclear explosions developed at an astonishing speed. By the mid-1960s, projects had been developed to create canals connecting northern and southern rivers, artificial harbors on the coast of the Arctic Ocean, and underground storage facilities for gas and oil. It seemed that atomic energy could solve any engineering problem. One of the most ambitious projects was the creation of the Pechora-Kolyma Canal, stretching over 600 kilometers using a chain of nuclear explosions. The plan was to use 167 nuclear charges with a total power of 3 megatons to lay a waterway through the tundra from Pechora to Kolyma. Fortunately, this project was never implemented. Experiments were conducted in the taiga of the Krasnoyarsk territory on the use of nuclear explosions for mineral extraction. The crater project involved the creation of quarries for open-pit mining using underground nuclear explosions. The theory was simple. A nuclear charge would destroy rock at great depths, creating a ready-made mine or quarry. In practice, all these experiments led to catastrophic environmental consequences. Each peaceful nuclear explosion created a zone of radiation contamination covering several square kilometers. Radioactive isotopes penetrated the groundwater, contaminated the soil, and spread through food chains over vast distances. The northern regions of the country, traditionally inhabited by indigenous peoples, were particularly affected. The Nenets, Evenks, Chukchi, and other northern ethnic groups suddenly found that their hunting grounds, reindeer pastures, and fishing areas had turned into radioactive deserts. Many families were forced to leave their homes forever. The program reached its peak in the 1970s, when several dozen peaceful nuclear explosions were carried out annually. A total of 124 explosions, with a total yield of about 7 megatons, were carried out under this program. The experiments were conducted in 21 regions of the country, from the Kola Peninsula to the Far East. One of the most tragic episodes was the Globus project to create an underground storage facility for gas condensate in the Orenburg region. A nuclear explosion with a yield of 2.5 kilotons was carried out on September 19, 1971, at a depth of 1.5 kilometers. The resulting cavity was supposed to serve as a reservoir, but it turned out to be so radioactive that it could not be used. Medical research on the impact of peaceful nuclear explosions on public health was extremely limited. Most of the data was classified as a state secret. Doctors were forbidden to link the illnesses of residents in the surrounding areas to radiation exposure. As a result, thousands of people did not receive the necessary treatment and were not even aware of the true causes of their illnesses. By the early 1980s, it had become clear that the peaceful nuclear explosion program was doing more harm than good. Environmental problems had reached such proportions that it was no longer possible to hide them. Public opinion in the country gradually turned against nuclear experiments. The last peaceful nuclear explosion in the USSR was carried out on October 6, 1988, as part of a project to extinguish a gas well blowout at a field in Turkmenistan. After that, the program was shut down under pressure from environmentalists and the public. But the radioactive legacy of peaceful nuclear explosions continues to affect the environment and human health to this day. The ecological disaster caused by nuclear tests in the taiga began with the very first explosion, but its true scale only became clear decades later. Radioactive isotopes released by hundreds of nuclear explosions have radically altered the ecosystems of vast territories, turning once flourishing forests into dead zones. The taiga, as an ecosystem, proved to be particularly vulnerable to radiation. Slow tree growth, long vegetation recovery cycles, and complex interrelationships between different animal and plant species meant that even small amounts of radiation contamination could have catastrophic long-term consequences. The first visible signs of ecological disaster appeared within days of the atmospheric tests. Within tens of kilometers of the epicenters of the explosions, trees began to lose their leaves and needles. Their trunks became covered with strange growths, and their bark peeled off in huge chunks. But the most frightening thing was that these changes were only the beginning of the long-term degradation of forest ecosystems. Radioactive fallout spread hundreds of kilometers from the test sites, in the direction of the wind. Cesium-137 and strontium-90 isotopes, which have a half-life of about 30 years, penetrated deep into the soil and became part of the biological cycles of the taiga. Plants absorbed these substances through their roots, animals ingested them with their food, and radiation gradually accumulated in all links of the food chain. Coniferous forests were particularly affected. Spruce, pine, fir, and larch, the main tree species of the Siberian taiga, proved to be extremely sensitive to radiation. In heavily contaminated areas, entire forest areas died within 1 to 2 years after the nuclear explosions, turning into so-called red forests, dead tree trunks with fallen reddish needles. Soil microorganisms, which play a key role in forest ecosystems, also died en masse from radiation exposure. This disrupted the natural processes of organic matter decomposition and nutrient cycling. Dead trees and plant debris did not decompose normally, creating huge piles of combustible material and increasing the risk of forest fires. The taiga's aquatic ecosystems were equally affected. Rivers, lakes, and swamps, which received radioactive fallout both directly from the atmosphere and through soil runoff, became sources of further contamination. Fish in these water bodies accumulated radioactive isotopes in their muscle tissue and internal organs, becoming dangerous for human consumption. Animal migration routes contributed to the spread of radioactive contamination over vast areas. Deer, moose, bears, and other large mammals roaming the taiga in search of food carried radioactive particles on their fur and in their bodies, contaminating new areas hundreds of kilometers away from the original sources of contamination. Birds, especially waterfowl and birds of prey, became indicators of the scale of the ecological disaster. Geese, ducks, swans, and cranes that nested in contaminated areas or flew through them during migration were found to have high concentrations of radioactive isotopes. Many of these birds died of radiation sickness or produced unviable offspring. Mushrooms and berries, which are essential components of the taiga food chain, became radiation concentrators. Some species of mushrooms are capable of accumulating radioactive substances in concentrations thousands of times higher than their content in the soil. Berries also intensively absorbed cesium and strontium isotopes, rendering vast areas unsuitable for traditional land use. The indigenous peoples of the north, who had lived in harmony with the taiga for centuries, were the first to face the consequences of radiation contamination. The Nenets, Evenks, Khanty, and other peoples, for whom hunting, fishing, and gathering were the basis of their existence, discovered that their traditional food had become deadly dangerous. But the official authorities concealed information about radiation contamination from them, condemning entire generations to slow poisoning. The processes of natural self-purification in the taiga are extremely slow. While in southern regions the biological half-life of radioactive substances is several years, in northern ecosystems it can stretch to decades. Low temperatures, a short growing season, and the specific nature of northern soil slow down the natural migration of radionuclides into the deeper layers of the earth. Lichens, the main food source for reindeer, have proven to be particularly effective accumulators of radioactive cesium. These primitive plants, which have no root system, absorb nutrients directly from the air and precipitation. As a result, the concentration of radioactive isotopes in lichens was dozens of times higher than their content in the soil, which made reindeer herding impossible in contaminated areas. Mutations in plants and animals became commonplace in areas of radioactive contamination. Trees with double trunks, plants with deformed leaves, animals with congenital deformities. All these signs of genetic disorders testified to the profound damage to ecosystems. However, scientific research into these phenomena was conducted in strict secrecy and was not published in the open press. The restoration of forests in areas of radioactive contamination was extremely slow and uneven. In some areas, young shoots appeared within a few years after radiation exposure, but these plants were often weakened and susceptible to various diseases. In the most affected areas, the process of reforestation took decades. The snow cover characteristic of the taiga created additional problems with the spread of radiation. Radioactive particles that fell on the snow during the winter concentrated in meltwater in the spring, creating local hotspots of high contamination. Spring floods carried this radioactive water throughout the region's river system. By the end of the 1980s, the environmental situation in the nuclear test areas had reached a critical point. Vast areas of taiga had been turned into radioactive deserts, where contamination levels exceeded safe limits by hundreds and thousands of times. The flora and fauna of these regions were irreversibly damaged, and the restoration of ecosystems could take centuries. The environmental disaster that began with the first nuclear explosions continues to unfold today, reminding us of the price humanity has paid for the nuclear arms race. 3 decades after the official end of nuclear testing, the radioactive legacy of the Soviet nuclear program continues to determine the environmental situation in vast territories. Recent studies show that the extent of contamination significantly exceeds initial estimates, and the processes of natural self-purification are proceeding much more slowly than expected. The Semipalatinsk test site remains one of the most radioactively contaminated places on the planet. According to data from Kazakh and international experts conducted in the 2000s, the radiation level in some areas of the former test site still exceeds background levels by 1,000 times. The area of land with dangerous levels of contamination covers more than 10,000 square kilometers. Plutonium-239 isotopes, which have a half-life of 24,000 years, are found in the soil at depths of up to several meters. These radioactive substances will pose a danger to the environment and humans for many millennia to come. In fact, huge areas have been taken out of economic circulation for an indefinite period of time. Groundwater in the areas of former test sites contains elevated concentrations of radioactive isotopes. Artesian wells located up to 100 kilometers from the epicenters of nuclear explosions show radiation levels that exceed permissible norms by tens of times. This creates serious water supply problems for the local population. Biological systems in areas of radioactive contamination show persistent genetic changes. Scientific studies conducted in the 1990s and 2000s have revealed an increased frequency of mutations in plants and animals living in these areas. Some species have become resistant to radiation, but at the expense of other vital functions. The Novaya Zemlya test site poses a particular problem due to its Arctic location. Permafrost preserves radioactive substances, preventing their natural migration into deeper soil layers. At the same time, global warming and the melting of permafrost could lead to the release of preserved radiation and its spread into the ocean. Arctic marine ecosystems still bear traces of radioactive contamination from the tests on Novaya Zemlya. Bottom sediments in the archipelago contain elevated concentrations of radioactive isotopes. Marine mammals, seals, walruses, polar bears accumulate these substances in their fatty tissue, making them potentially dangerous for the traditional hunting practices of the Arctic's indigenous peoples. Areas where peaceful nuclear explosions were conducted also remain a source of radiation hazard. Artificial reservoirs created by nuclear charges are still unusable. Underground cavities formed by explosions have become reservoirs of highly radioactive substances that slowly seep into the environment. International organizations, including the International Atomic Energy Agency, regularly monitor the radiation situation in the territories of former Soviet test sites. Their data confirm that the problem of radioactive contamination is long-term and requires constant monitoring. Attempts to reclaim contaminated areas have had limited results. Soil decontamination technologies are only effective for the surface layer and require enormous financial costs. Complete decontamination of areas from radioactive contamination is technically impossible with the current level of technology. Climate change exacerbates the problem of the radioactive legacy. Frequent droughts and forest fires contribute to the long-distance transport of radioactive particles from contaminated areas. Wind erosion lifts radioactive dust into the air, causing secondary contamination of previously clean areas. The economic losses from radioactive contamination of territories are estimated at hundreds of billions of dollars. The cost of land taken out of economic circulation, the cost of medical care for the affected population, and the cost of monitoring and eliminating the consequences all constitute a huge financial burden for the successor states of the USSR. Modern remote sensing technologies provide a more accurate picture of radioactive contamination. Satellite images and aerial photography reveal areas of abnormal vegetation, which serve as indicators of radiation exposure. These data show that the actual extent of contamination exceeds the official estimates of the Soviet period. The medical consequences of nuclear testing in the Taiga did not manifest themselves immediately, but their impact on the health of the population is still felt today. Generations of people who lived near the test sites or were exposed to radioactive fallout suffer from diseases that official medicine has long refused to link to radiation exposure. The population living in the Semipalatinsk test site area became unwitting participants in the largest medical experiment in human history. More than 1 million people were exposed to radiation to varying degrees during the years the test site was in operation. But systematic medical research on these people began only after the test site was closed, when it was already impossible to change anything. The first signs of mass radiation damage to the population became apparent as early as the 1950s. Doctors at local hospitals noted a sharp increase in the number of cancer cases, especially blood, thyroid, and lung cancer. However, they were forbidden from mentioning the connection between these diseases and nuclear testing in medical records. Children born to families affected by radiation showed a high incidence of congenital malformations. Statistics showed a 5 to 10-fold increase in pathologies such as spina bifida, heart defects, mental retardation, and limb deformities. Many of these children did not live to see adulthood. Women of reproductive age were particularly affected. They experienced a sharp increase in the frequency of miscarriages, stillbirths, and infertility. Maternal mortality in areas adjacent to the test sites exceeded the national average several times over. But all these statistics were carefully concealed and not published in the open press. The human endocrine system proved to be particularly sensitive to radiation exposure. The thyroid gland, which actively absorbs radioactive iodine, was the first to suffer. Thyroid diseases became endemic in the areas of nuclear testing, affecting up to 70% of the population in some settlements. The immune systems of people exposed to chronic radiation showed serious disturbances. Increased susceptibility to infectious diseases, autoimmune disorders, premature aging, all these symptoms became characteristic of the population of contaminated areas. Mental disorders are also linked to radiation exposure. Studies have shown an increased incidence of depression, anxiety disorders, and other mental health problems among residents of nuclear test areas. Some scientists attribute this not only to the direct effects of radiation on the nervous system, but also to the psychological stress of being aware of the radiation hazard. Participants in the Trotsky exercises and their descendants represent a particular risk group. Medical observations begun in the 1990s have shown that among former military personnel who took part in nuclear exercises, cancer occurs 3 to 4 times more frequently than in control groups. The genetic consequences of radiation exposure are evident not only in the first generation, but also in the second and third generations. The grandchildren and great-grandchildren of people who were exposed to radiation show an increased incidence of genetic diseases, even if they have never lived in contaminated areas. This indicates profound damage to the human genetic apparatus. The healthcare system in the areas of nuclear testing was completely unprepared to deal with radiation damage. Doctors did not have the necessary knowledge and equipment to diagnose and treat radiation sickness. Many patients received inadequate treatment or were left without medical care altogether. Epidemiological studies conducted by international organizations in the 1990s and 2000s confirmed the link between nuclear testing and increased morbidity among the population. However, the full picture of the medical consequences has not yet been restored due to the concealment of data during the Soviet period. Modern technologies allow for a more accurate assessment of the extent of radiation damage to the population. Molecular genetic studies identify specific markers of radiation exposure in human blood, which helps to establish a link between diseases and radiation exposure even decades later. The problem of the medical consequences of nuclear testing remains relevant today. The descendants of irradiated people need specialized medical observation and treatment. The creation of registries of victims, the development of methods for the early diagnosis of radiation-induced diseases, and the improvement of treatment methods, all these tasks require significant resources and international cooperation. The archives of the Soviet nuclear program contain thousands of documents that remain classified to this day. These materials contain detailed information about the actual extent of radiation contamination, medical studies of the affected population, and the environmental consequences of nuclear testing. This data has been concealed for more than 7 decades, making it impossible to fully assess the damage caused by the Soviet nuclear program. The secrecy system created around nuclear testing was unprecedented in its scope. Documents were classified according to several levels of access: top secret, of special importance, and for official use only. Many materials had additional classifications that restricted access to them even among the country's top leadership. The first attempts to declassify the archives were made during the period of perestroika in the late 1980s. However, these attempts were extremely limited and mainly concerned the technical aspects of nuclear testing. Data on the medical and environmental consequences remained closed to researchers and the public. Of particular value are the medical archives containing the results of examinations of the population living near the test sites. Soviet doctors and biologists kept detailed records of the health of residents in contaminated areas. But this data was intended for internal use only and was never published. The archives of the Institute of Biophysics contain unique materials on the effects of radiation on various biological objects. Experiments were conducted not only on laboratory animals, but also on agricultural crops, wild flora, and fauna. The results of these studies could shed light on the mechanisms of radiation damage to ecosystems. Ministry of Defense documents contain detailed reports on nuclear tests, including data on meteorological conditions, wind direction, and the spread of radioactive clouds. This information is critical to understanding which areas were contaminated and to what extent. The archives of closed cities, Arzamas 16, Chelyabinsk 70, Tomsk 7, and other centers of the nuclear program, contain technical documentation on the production, transportation, and disposal of nuclear charges. Some of these materials relate to accidents and incidents that were never made public. Documents on the peaceful nuclear explosions program are of particular importance. The archives contain plans for grandiose projects to change the geography of the country with the help of atomic energy, most of which, fortunately, were not implemented. But even the projects that were implemented caused enormous damage to the environment. International organizations have repeatedly appealed to the Russian authorities to declassify the archives of the nuclear program. However, most of these appeals remain unanswered. References to national security are used to conceal information that is of exclusively historical and scientific significance. Some documents have become available to researchers thanks to the activities of dissidents and human rights activists. In the 1990s, a number of former nuclear industry employees passed copies of secret materials to journalists and scientists. These leaks provided the first reliable data on the extent of radiation contamination. The digitization of archives in recent years has opened up new opportunities for researchers. However, access to digitized documents remains strictly limited. Most materials are only available to government employees and are subject to numerous restrictions on use. Families of those affected by nuclear testing continue to fight for access to their relatives' medical records. In many cases, people are unable to obtain information about the radiation doses their parents or grandparents received, making it difficult to obtain medical care and compensation. Full declassification of the archives of the Soviet nuclear program could radically change our understanding of the environmental and medical consequences of nuclear testing. This information is essential for developing effective programs to help victims and prevent similar disasters in the future. However, political considerations still prevail over the interests of science and the public. International experts estimate that the classified archives may contain information on hundreds of unknown incidents related to nuclear testing. The full picture of the radiation impact on the population and the environment will remain incomplete as long as these documents remain inaccessible to researchers. The international community knew much more about the Soviet nuclear testing program than is commonly believed. Western intelligence services closely monitored the USSR's nuclear activity, but chose to remain silent about the environmental and humanitarian consequences of these experiments. This silence became part of a global game in which geopolitical interests took precedence over the fates of millions of people. American spy satellites of the Corona series began photographing Soviet nuclear test sites in the early 1960s. High-resolution images allowed for detailed study of the infrastructure of the test sites, assessment of the power of the explosions, and tracking of their consequences. The CIA had accurate data on the number and nature of Soviet nuclear tests. Seismological stations around the world recorded underground nuclear explosions in the USSR in near real time. The international monitoring system made it possible to determine not only the location and time of the explosion, but also its approximate power. This data was regularly transmitted to Western governments. NATO's radiation monitoring system constantly tracked radioactive emissions from Soviet nuclear tests. Sensors installed in Western Europe, Japan, and other countries recorded an increase in radiation levels after each atmospheric explosion in the USSR. However, this information was carefully concealed from the public so as not to cause panic and interfere with diplomatic processes. The scientific community in Western countries had access to some data on Soviet nuclear tests through international scientific programs. Meteorologists, geophysicists, and biologists exchanged information with their Soviet colleagues, but at the same time observed unspoken rules about the inadmissibility of criticizing military programs. International organizations played a special role in concealing information. The International Atomic Energy Agency, established in 1957, was officially concerned with the peaceful use of atomic energy, but in fact contributed to the legitimization of the nuclear programs of the great powers. Diplomatic channels were used to transmit information about Soviet nuclear tests between Western countries. Embassies and consulates in regions adjacent to Soviet test sites regularly reported strange phenomena associated with nuclear explosions. But these reports were classified and did not reach the public domain. European countries, especially Sweden and Norway, regularly recorded radioactive fallout from Soviet tests on their territory. Their meteorological services kept detailed records of radiation levels in the air, soil, and water bodies, but governments preferred not to raise the issue at the international level, fearing a deterioration in relations with the USSR. The media in Western countries received information about Soviet nuclear tests from their intelligence services, but only published general reports about the fact that the tests were being conducted. Details about the radiation contamination of territories and the suffering of the population were hushed up. International environmental organizations such as Greenpeace began to openly criticize nuclear testing only in the 1970s. Until then, the environmental movement was not sufficiently organized to counter the powerful nuclear industry lobby. The treaty banning nuclear weapon tests in the atmosphere, in outer space, and underwater, signed in 1963, was the first international document to restrict nuclear testing. However, it did not ban underground explosions, which continued for another quarter of a century. The People's Republic of China, which also conducted nuclear tests in the Gobi Desert, maintained a tacit agreement of silence with other nuclear powers. Despite political differences between the USSR and China, they acted in solidarity on issues related to concealing the environmental consequences of nuclear programs. International medical organizations had data on the increase in cancer incidence in regions exposed to radiation, but did not actively investigate the problem. The World Health Organization preferred not to interfere in the internal affairs of member states. The role of the international media in concealing the truth about the consequences of nuclear testing was ambiguous. On the one hand, journalists tried to cover nuclear issues, but on the other hand, they faced obstacles from both Soviet and Western authorities. The international silence on the environmental and humanitarian consequences of nuclear testing continued until the end of the Cold War. It was only in the 1990s, when the geopolitical situation changed dramatically, that the international community began to openly discuss the legacy of the nuclear arms race. But by that time, the damage had already been done, and its consequences continue to be felt to this day. Modern scientific research is gradually lifting the veil of secrecy over the true scale of the ecological disaster caused by nuclear testing in the Taiga. Using the latest technologies in analysis, satellite monitoring, and molecular biology, scientists are gaining an increasingly complete picture of the long-term consequences of the Soviet nuclear program. International research projects launched in the 2000s made it possible for the first time to conduct a comprehensive assessment of radiation contamination in these areas. Joint expeditions by Russian, Kazakh, American, and European scientists use modern equipment to measure radiation levels with a precision that was unattainable in Soviet times. The results of these studies were shocking even to experts. The extent of radiation contamination significantly exceeded official estimates from the Soviet period. Areas with dangerous levels of radiation turned out to be 2 to 3 times larger than previously thought, and the concentration of long-lived isotopes in some areas reaches levels comparable to those in the Chernobyl exclusion zone. Genomic studies of plants and animals living in areas of radiation contamination reveal persistent genetic changes that are passed down from generation to generation. Some species have acquired unique adaptations to the radiation environment, but at the cost of losing other important biological functions. Paleoecological studies allow us to reconstruct the picture of environmental changes since the beginning of nuclear testing. Analysis of tree rings, lake sediments, and peat bogs shows how radiation has affected taiga ecosystems over decades. High-resolution satellite imagery makes it possible to track changes in vegetation cover in areas of radiation contamination. Multispectral images reveal areas with abnormal vegetation characteristics, which serve as indicators of radiation exposure. Epidemiological studies of the current population living in former test site areas confirm an increased incidence of cancer and genetic diseases. Molecular genetic analysis can detect specific markers of radiation exposure even decades after irradiation. Hydrogeological studies show that groundwater in nuclear test areas contains elevated concentrations of radioactive isotopes at depths of up to several hundred meters. This poses a long-term threat to water supplies and requires constant monitoring. Climate models demonstrate how global warming can affect the migration of radioactive substances. The melting of permafrost in Arctic regions could lead to the release of stored radiation and its spread into the ocean. New decontamination technologies developed after the Chernobyl disaster are being tested in former Soviet testing grounds. Bioremediation using special microorganisms and plants has shown some success, but it will take decades to have a significant effect. Research on the effects of low doses of radiation on biological systems is revising traditional ideas about radiation safety. It turns out that prolonged exposure to even small doses can cause serious genetic disorders. International scientific programs to study the consequences of nuclear testing face political obstacles. Access to some areas is restricted, and obtaining research permits requires complex bureaucratic procedures. Digital modeling of the spread of radioactive substances allows the reconstruction of contamination migration paths from the time of testing. These models help predict future changes in the radiation situation and plan measures to protect the population. Sociological studies examine the psychological impact of the radiation threat on the population. Fear of an invisible danger, uncertainty about the health of children and grandchildren, and distrust of official information all seriously affect people's quality of life. Economic studies attempt to assess the total cost of damage from nuclear tests. In addition to the direct costs of cleaning up the aftermath, losses from land being taken out of economic circulation, the cost of medical care for victims, and compensation are also taken into account. Modern science has all the necessary tools to fully study the consequences of nuclear testing in the taiga. However, political restrictions and lack of funding hinder the implementation of comprehensive research programs. The full picture of the ecological disaster will only be restored when scientific interests prevail over political considerations. The struggle for the truth about the consequences of nuclear testing in the Taiga began back in Soviet times, when individual scientists and activists risked their freedom and their lives to bring information about the scale of the ecological disaster to the public's attention. Their efforts laid the foundation for a movement that ultimately led to the cessation of nuclear testing and the beginning of the process of declassifying archives. Andrei Sakharov, one of the creators of Soviet thermonuclear weapons, was the first to openly oppose nuclear testing. As early as the 1960s, he warned of the catastrophic consequences of atmospheric radiation contamination and called for an end to atmospheric explosions. His scientific authority and moral stance played a key role in changing public opinion. In the 1970s, a group of Soviet physicists and biologists began secretly documenting the environmental consequences of nuclear testing. They collected data on radiation contamination of territories, photographed dead forests and deformed animals, and recorded the testimonies of local residents. These materials were passed on to Western journalists and human rights activists. Olzas Suleimanov, a Kazakh poet and public figure, became a symbol of the struggle against the Semipalatinsk test site. On February 28, 1989, he appeared on Kazakh television with a call to close the test site. His speech sparked the creation of the mass anti-nuclear movement, Novaya Semipalatinsk. The Novaya Semipalatinsk movement united victims of nuclear testing in the USSR and the United States. Activists from Kazakhstan, Russia, and America coordinated their actions, exchanged information, and jointly put pressure on governments. This was the first example of an international environmental movement during the Cold War. Doctors from areas adjacent to the test sites played a special role in exposing the medical consequences of nuclear testing. Despite bans and threats, some of them kept secret statistics on cancer and congenital malformations. Their data became important evidence of the link between radiation and increased morbidity. Investigative journalists gradually pieced together a picture of the nuclear experiments using leaks, eyewitness accounts, and analysis of open sources. Their publications in the independent press in the late 1980s were the first to inform the general public about the true scale of the problem. Veterans of nuclear tests, who had long remained silent about their participation in secret programs, began to form associations and demand recognition of their status as victims of radiation. Their testimonies became an important source of information about the technical details of the tests and their consequences. International environmental organizations gradually joined the fight against nuclear testing. Greenpeace organized expeditions to former test sites, documented environmental damage, and drew the attention of the world media to the problem of the radiation legacy. Human rights activists fought for the rights of people affected by nuclear testing. They sought compensation for those exposed to radiation, medical care for the sick, and recognition of the state's responsibility for the damage caused. This work continues to this day in the courts of various countries. Dissident scientists passed on secret information about the Soviet nuclear program to the West, risking repression. Their materials were used by international organizations to pressure the USSR to stop testing and begin the process of declassification. Activists from the indigenous peoples of the North and Siberia raised issues about the violation of their traditional rights and the destruction of their way of life. Their voices gradually became heard in international organizations working to protect the rights of indigenous peoples. Information technology in the 1990s and 2000s provided new opportunities for the fight for truth. The Internet allowed activists to coordinate their actions, exchange information, and draw international attention to the problem. Specialized websites, databases of victims, and document archives were created. Parliamentary investigations in the successor states of the USSR became an important tool for revealing the truth about nuclear testing. Deputies gained access to previously classified materials and published reports on the extent of environmental and medical damage. Lawsuits against state organizations responsible for conducting nuclear tests became a way to achieve justice and compensation for victims. Although most claims remain unsatisfied, the very fact that they were filed draws public attention to the problem. The struggle for the truth about the consequences of nuclear testing continues to this day. A new generation of activists is using modern technology and methods to document environmental damage, search for classified documents, and pressure the authorities to fully disclose information about the nuclear legacy of the past. The legacy of the atomic age left by nuclear testing in the Taiga will affect the life of our planet for many centuries to come. Radioactive isotopes with half-lives of thousands of years have turned vast areas into exclusion zones, creating an environmental problem on a planetary scale. The experience of the Soviet nuclear program has been a harsh lesson in the consequences of irresponsible use of nuclear energy. Current estimates show that the complete restoration of taiga ecosystems in the most affected areas could take between 300 and 1,000 years. This means that the consequences of nuclear testing will be felt not only by our children and grandchildren, but also by dozens of future generations. Such a long-term perspective forces us to rethink the very concept of environmental responsibility. The economic consequences of the radiation legacy are estimated at trillions of dollars. The cost of land permanently removed from economic use, the cost of medical care for affected generations, and the cost of ongoing radiation monitoring all represent a colossal financial burden for the global community. Remediation technologies developed to eliminate the consequences of nuclear accidents have shown limited effectiveness when working with areas contaminated as a result of testing. The scale of contamination is so great, and the concentrations of radioactive substances so high that complete decontamination of the areas remains technically impossible. Climate change exacerbates the problem of the radioactive legacy. The melting of permafrost in the Arctic could lead to the release of radioactive substances that have been preserved in the ice for decades. Increasingly frequent forest fires contribute to the long-distance transport of radioactive particles, causing secondary contamination of previously clean areas. Medical research in recent years has identified new mechanisms by which radiation affects the human genetic apparatus. Epigenetic changes caused by radiation can be passed on through several generations, creating long-term health risks for the descendants of irradiated individuals. The social consequences of nuclear testing are manifested in the destruction of the traditional way of life of indigenous peoples, the forced migration of populations from contaminated areas, and psychological trauma passed down from generation to generation. Restoring the social fabric in the affected regions requires comprehensive support programs. International law is gradually recognizing environmental crimes alongside war crimes and crimes against humanity. Nuclear tests conducted without consideration of environmental consequences can be considered crimes against future generations. Educational programs on the consequences of nuclear testing are becoming an important tool for preventing the recurrence of such disasters. Studying the history of the Soviet nuclear program should become a mandatory part of environmental education so that future generations understand the price of irresponsible use of nuclear technology. International cooperation in the field of eliminating the consequences of nuclear testing is developing extremely slowly. Political contradictions and economic considerations hinder the creation of effective mechanisms for international assistance to affected regions. New generations of scientists, unencumbered by the ideological constraints of the past, are able to objectively assess the scale of the environmental disaster. Their research is gradually piecing together a complete picture of the impact of nuclear testing on the environment and human health. Technological advances are opening up new opportunities for monitoring the radiation situation and eliminating the consequences of contamination. Drones, satellites, automatic monitoring stations, and robotic decontamination systems can significantly speed up the process of restoring the affected areas. The memory of the victims of nuclear testing is becoming an important element of historical consciousness. Memorials, museums, and documentary films preserve evidence of the tragedy for future generations, warning against the inadmissibility of repeating such experiments on nature and humans. The ethical dilemmas associated with the use of nuclear technology remain relevant today. The balance between the potential benefits of nuclear energy and the risks of radiation contamination requires constant public scrutiny and international regulation. The future of the planet largely depends on whether humanity can learn from the tragic experience of nuclear testing in the Taiga. The legacy of the atomic age reminds us of the need for a responsible attitude toward technologies that can change the face of our planet forever.